Hello everyone, I'm Saurabh and I'll be giving my project presentation for EEL 6825 pattern recognition on the topic iris recognition for authentication and identification. Now, biometrics is a very good way to make sure that a person is who he is or who he claims to be. Traditional methods for identification and authorization are prone to data breaches and are becoming more and more complicated each and every day. In comes iris scanning. Iris scanning is one of the best methods of biometrics verification and it relies upon mathematical pattern recognition techniques. It is fast, contactless, non invasive, and known for its accuracy. Iris biometrics. Iris is basically the externally visible part of our eye. It is the colored ring around the pupil. Iris is stable throughout the life, and it is one of the reasons why we pick upon iris as compared to the other biometrics because it is stable. Whereas in the case of fingerprints, they might change or deteriorate during your lifetime. Now, why only iris recognition? Because we have other methods of biometrics, fingerprints, etc. But why only iris? Iris patterns are unique. Each and every individual on this earth has a different iris pattern. It cannot be same. And it is because of the fact that during the embryonic gestation, the iris patterns are formed. The iris recognition is non-contact approach. It is non-invasive as compared to fingerprint. And the simplicity and ease of using iris recognition is very simple. Now, before we move on, let's take an overview of a system model. First of all, we take an image. The image in our project is taken from Chinese Academy of Sciences Institute of Automation, CASIA, and this is the image acquisition stage. After the image is taken of the left or the right eye, iris localization is done. In the localization part, we take out the pupil from the eye, from the image, and remove all the eyelids and all the parts that we do not need. We do not need. After that, normalization is done, and unwrapping is done. And after encoding using Gabor filter, we calculate the Hamming distance between the two images to find out how closely related they are, and then we make a decision based on our Hamming distance. Segmentation. Segmentation is isolating the actual iris region from the eyelids and the eyelashes because we are not interested in the eyelashes part of the eye. We are only interested in finding out what the pattern of the pupil or what the pattern of the iris is to get a template from the iris and match it with other templates. Now, various methods have been proposed for segmentation, and two of the methods have been discussed in the paper: hue transform and Domain's integral differential operator. But I have seen and have also mentioned in my conclusion the problems with the segmentation is that the orientation of the eye should be same. If two images are taken at a different angle or if they are taken at a varying distance, then it is difficult for the program to find out if both of them belong to the same eye or not. Also, if the image is taken in low contrast, there might be some difficulties. Hue transform. Hue transform is a general algorithm used to find the boundaries of the geometric objects such as circles present in an image. And in our case, we need to find out the iris in our eye. We will use the hue transform to find the circles present in our image. To find the circles, we will use the circular hue transform to find the radii and the center of the pupil. The algorithm uses broadcasting for the points lying at a different area of the circle. We find the radius and centers using the following equation of x square plus y square minus r square equal to 0. Now, the problem with the hue transform method it is that it is difficult to optimize threshold value for edge detection, and computationally it is expensive due to brute force, and it may not be suitable for real-time application. But in our project, this will do. Now, moving on to Domain's integral differential method. To find the center Cartesian coordinates and radius, we use the Domain's integral differential operator. We need to ignore the eyelids and focus only on the iris and the pupil part. As we can see, using this equation, we can do that. The equation above is used to find the specific regions in the eye, where I x comma y is the eye image and r is the radius. And if you look carefully, we can see that Domain's integral differential is just a variation of the hue transformation, but it overcomes the threshold problems in a hue transformation. As we can see, a hue transformation has threshold problems and it overcomes that. Now, localization. Now, before we do localization of an image, the localization is it in itself divided into four categories, four levels. The first one is separation of pupil from the region of eye image, and determining of the pupil coordinates, determining of iris edges based on previously discussed principles, and finally removing the unwanted part and getting the segmented part of the image. Let's begin with the normalization. After the image is segmented, we cannot just compare it with other images in the database. We need to normalize it to compare it with the others. In the process of normalization, the iris region is transformed to fix the dimensions of the pupil. Since the dimensions of the pupil are now fixed in the normalization, we can compare it with other images. We need to do this because we need fixed dimensions. We need each and every image to have fixed dimensions so that we can compare to each other. Normalization basically produces iris region nullifying the effect of dimensional inconsistencies. That is, a fixed dimensional image for each and every image that we take as an input. The algorithm involves polar conversion of the iris image. We convert our planar coordinates into polar coordinates to give a fixed dimension of our image to the image. Next is Dogman's rubber sheet model. So as I said earlier, in normalization, the algorithm involves polar conversion of the iris image, and this is exactly what is done by Dogman's rubber sheet model. The model does not compensate for rotational inconsistencies, but here what the model does. The points we have after the hue transform are in the Cartesian format, but Dogman's rubber sheet model transforms them into pair of polar coordinates r comma theta, as it can be seen in this image. Feature extraction. After my coordinates are changed from Cartesian to polar, the next feature encoding, that is feature extraction. We need to find the most distinctive feature in a person's eye so that we can say it belongs to someone unique. So only the unique and distinctive features of an eye must be encoded so that the comparisons between the templates can be made. It generates a unique mathematical templates for iris images, and they are basically two widely used method for extraction of features. The first one is Gabon filter and the second one is Haar wavelets. Both of them will be discussed later on. Now, in wavelet in Haar wavelet transform is used to extract distinctive and unique values from its iris. We say Haar wavelet is our most simple wavelet and it is not continuous. It cannot be differentiated. Matching. To check if two templates are same or not, the template generated during the feature extraction mechanism is checked simultaneously side by side with other templates. Some of the significant matching algorithms we use are Hamming distance classifier, weighted Euclidean distances, and Canberra distance matrix. Hamming distance. To check how many bits are same between two numbers, we use the Hamming distance. Using this, we can conclude if two patterns were generated from different irises or from the same irises. How do we conclude that? If the two templates, if the two patterns are same, the Hamming distance will be 0.05, that is half. And what does that indicate? It indicates that the probability of each of the image to occur is equally likely, that is 1 by 2, 1 by 2. There is an equally possibility of happening both of the two templates. The Hamming distance can be calculated by this formula, and we can see the result given by Hamming distance determines if there is an iris match or there is not a match. If our Hamming distance is less than 0.2, then it is an iris match, and if it is not less than 0.2, it is greater than 0.2, it is not a match. Now I'll be moving on to the demo of this project. Let's see how this project actually works.